I'm Elwyn Berlekamp, and now I want to tell you about a fascinating game called Amazons and some of the mathematics behind it. An Amazon is an immortal chess queen. It can be moved as far as desired in any of 8 directions. After moving, it must shoot an arrow. The arrow may also move like a chess queen, and it burns out the square of the board on which it lands. Squares which are burned out block everything. You cannot move an Amazon over a burned out square, nor can you shoot an arrow over a burned out square. Although we are interested in Amazons from any starting position, the game is officially played on a 10 by 10 board in which each side has 4 Amazons in this starting position. However, we'll now look at a shorter game played on the smaller 8 by 8 board. In this game, black moves first and the players alternate turns. The game of Amazons was invented in 1988 by Walter Zamkauskas in Argentina. It was first published in Spanish in 1992 and in English in 1994. The first international tournament was played by fax in 1994 and 1995 between Argentina and the U.S. That tournament ended in a 3-3 tie. There are now several Amazons playing computer programs which compete against each other in the Computer Olympiad. In the game we've been watching, the board is now partitioned into several disjoint areas. Each subsequent move must burn up a square in her own territory. It's now black's turn. And white plays 2, and they start burning up squares, each in the territory that they're on. Whoever runs out of squares to burn up first will lose. In this case, it's now black's turn, and she is unable to move, and so white wins. We could count the score earlier. Here's the position in that game after 27 moves had been played. 27 squares are burned out. 6 are occupied by Amazons, and the other 31 squares are empty. In this particular position, all of the empty squares can now be claimed by one side or the other. Black controls 15 empty squares, white controls 16. So black has 15 moves remaining, but white has 16. So white can win no matter whose turn it is to play next. In some positions, a player may control more territory than she can ever fill with arrows. Here is an example in which black controls 2 empty squares, but can play only 1 move. Such a territory is called defective. One way to verify that a territory is not defective is to demonstrate a path along which an Amazon can plod through it. Each plodding move advances a single square, like a chess king, and then shoots the arrow back into the square it just left. Here we see plodding counts which demonstrate that 4 of the 5 regions are not defective. Although black is unable to make 2 consecutive plodding moves in the region at the top left, she can still make 2 moves there. 1, 2. So this territory is not defective. Here are the final counts, as we've seen before. It is often convenient to call our players left and right, rather than black and white. Left is black, denoted by the letter L. White is right, denoted by the letter R. Being from Berkeley, we view L as positive. Our rival, Stanford, is denoted by R and is negative. It is also convenient to call each position a game. This focuses our attention on subsequent play. Prior history, including whatever might once have been some official or unofficial starting position, is no longer relevant. We say that a game is positive if and only if left can win, no matter whose turn it is to play next. or negative if right can win, or 0 if either left or right can win if it is the opponent's turn, or fuzzy if either left or right can win if it is their turn to play next. These conditions for the outcome of the game G can be rewritten with mathematical symbols. When the first player can win, our symbol summarizes the fact that G is not positive, nor negative, nor equal to 0. These examples show the simplest case of each of the 4 outcome classes. On the third example, the rules require the next player to move, but since she has no legal move, she loses. The value is 0. In the fourth example, the first player will make the only legal move, which ends the game and wins. This position, in which either player can move only to 0, is called star. It is denoted by an asterisk. One immediate consequence of our outcome definitions is that the game is greater than or equal to 0 if and only if left playing second can win. If it is positive, she wins because she is left. If it is 0, she wins because she gets to play second. Now suppose we have a game such as the following, which is the sum of 2 distinct games. When the game G is played alone, it can last at most 4 moves because there are only 4 empty squares. Although white has many possible strategies, black, moving second, can defeat all of them. Hence, G is greater than or equal to 0. Similarly, black playing second can also win game H when it is played alone. This is a special case of the more general situation in which we have 2 games each greater than or equal to 0. We now consider the sum game G plus H, indicated by a single line across the bottom of the sketch. Suppose white plays in H, changing it to some H prime, which cannot be less than or equal to 0. Black can respond by using her winning strategy in H alone to select a move to some game H double prime, which again is greater than or equal to 0. Perhaps white next plays in G, changing it to some G prime, which cannot be less than or equal to 0. Black can respond by using her winning strategy in G alone to select a move to some game G double prime, which again is greater than or equal to 0. In this manner, black ensures that she can get the last move in G and the last move in H, and hence the overall last move in the sum G plus H. So, left going second can win, proving that G plus H is greater than or equal to 0. So in general, if G and H are games, and if G is greater than or equal to 0, and H is greater than or equal to 0, then G plus H is also greater than or equal to 0. Similarly, if G is less equal to 0, and H is less equal to 0, then G plus H is also less equal to 0. So our definitions of inequalities for games behave as in conventional arithmetic. Let's now examine some more very simple Amazon's games. This game has at most 2 moves remaining. It is easily seen to be positive because left can win no matter whose turn it is to play next. Let's call this game X. Let's add it to itself. Let's also add in a -1. On the first 2 moves in this game, black and white will each get 1 move on one of the leftmost components in either order. The value of what remains will be 0 plus 1 minus 1. Since this sums to 0, second player can win. Hence, x plus minus 1 equals 0, from which it is reasonable to conclude that x equals a half. So in this region, black has exactly a half point of territory. Suppose we next imagine a similar region in which the colors of black and white are reversed. Either player, going second, can copy her opponent's move on the other region and thereby win by maintaining the symmetry. Hence, we have a game whose value is minus a half. Here's the position of the game of segment 1, after only 23 moves had been played. The values of the regions in the northeast, southeast, and southwest are already integers. But what is the value of the region in the northwest? Suppose we add it to -1/2. With patience, you can show that the value of the total game is 0. Hence, the challenging region in the northwest must be a net half move for black. Although there are other combinatorial game values which satisfy the equation x plus x equals 1, they are more complicated than numbers, and they are not applicable in this simple case. The total value of the board is -1/2, and since this is negative, white can win no matter whose turn it is to play next. Let's conclude this segment by revealing what happens after black's next move in the northwest corner. We get a game that can be shown to satisfy the equation x plus x -1/2 equals 0. So this x is 1/4. It turns out that this x is a number, which means that its value must be 1/4.